Greeting professors and friends, we are Group 1 SC5. Our mini project is on car resale price. This will be the table of contents for our presentation. We have identified two key project motivations from real-world problems. When looking at car listings, firstly, how do consumers judge if a price is fair for a certain car? Secondly, when looking deeper into the statistics of a car, how should consumers translate different price variables and adjust their prices accordingly? We use the used car dataset from Kaggle, which periodically scrapes Craigslist US for used car listings. Basic EDA tells us that there are 4 to 6K listings with 26 columns. However, some of the columns are immediately useless since they hold no important information that can be further analyzed. A quick summary is shown here. Price is the dependent variable that we would like to predict, so we have done further EDA on it. One can see that there is a clear difference between the mean and median. This suggests the presence of extreme outliers which can sway the mean price, and further data cleaning will be required to remove these outliers. After carrying out further EDA, we have chosen to ignore these columns as well. There are too many missing values for the country columns, and there are too many unique values for the model column to do anything useful. After plotting a correlation matrix for the numeric variables for the listings of the top 6 manufacturers, we found that latitude and longitude had low correlation with price across the board, and we have decided to ignore it. As for cylinder and type, because so many listings have a value of other for these columns, it is hard to do any data cleaning for this without making sweeping generalizations. The data under the paint color is too general to carry out any meaningful analysis. One useful variable to consider is the manufacturer. When seeing the average price across different manufacturers, one can see the huge disparity between different brands. This is because brands like Mercedes-Benz produce expensive luxury cars, while brands like Mitsubishi produce cheaper economical cars. Hence, how does the manufacturer brand affect a car resale value? Repeating this thought process across different columns allow us to identify which columns are useful for price predictions and which are not. A summary is shown here. Our problem definition is shown on the slide, and we have split it into 3 subproblems which we will solve to help us achieve a final solution. With the problem statement defined, we will proceed to clean the data to train our machine models. Overall, we have raised the correlation of numeric variables, and we have applied feature engineering techniques to improve efficacy of our trained model. We first tackled outliers which were outside the whiskers of the box plot. We also had variables such as price and odometer which were right skewed. So we tried performing a logarithmic transformation to give it a more symmetric distribution. We also applied imputation techniques as we found that there were over 30% of missing data in some of the variables which did not give a strong enough justification to drop from our dataset. For numeric variables, we imputed the median, and for categorical, we imputed a not known category. A new feature engineering technique we applied that was not taught in lectures was to use discretization, where we group numeric variable price into larger bins. We reduced the precision of price prediction, but since our problem definition was to explore how the variables affect the resale price and not to predict a resale price, we are able to reduce the number of nodes generated by the model during the machine learning phase. We will now delve into the core analysis of our project. Here we discuss the 2 subproblems we tried to solve with machine learning. We will be going through tree regressor, linear regression, followed by tree classifier, and we will analyze how discretization changed the way the model responded. The format moving forward will be such that images on the left side of the slide is the model fitted with price as numeric, and on the right will be price as categorical, range 1 to 10. And we can see evidently that changing the response variable does not change the feature importance for a tree regressor model. What is interesting is that the model returns significantly higher explained variance, indicating a better fit. To note that since the response variable is different, we cannot directly compare other statistics such as MSE here. We also found that feature importance for linear regression models did change when using a different response variable, where some variables, such as if a car is using diesel or not, could play a higher importance in predicting price of a car. Overall, we see that the explained variance for price as categorical resulted in a better fit on both test and train set for linear regression. But we do note that the negative prediction returned by the linear regressor model suggests that linear regression may not be a good model to use for prediction of resale price of a car, since I can't possibly be paying money to someone I am selling my car to. Next, we access the classifier models since we are using price as a categorical variable, and we can see that the model is not performing well for the test set. We can also see that the confusion matrix here highlights how poor the prediction was for the test set on the right side of the slide. We do note that the classifier model plays a different percentage of feature importance compared to its regressor counterpart, where the classifier had 17% significance for year, while year had 56% significance in the regressor model. So the takeaway from subproblem 1 and 2. Different models have variables with different feature importance allocated, and using price as a categorical variable gave a better model fit compared to price as numeric, and this was to be expected since having larger bins means smaller residual sum of squares, which implies larger R square. Overall, classifier is more suited to predicting price when it is categorical, but the F1 score obtained is low, so a better model could have been explored, which leads us to our subproblem 3. Is there a better model we can use to predict the price of a car? So we have learned that decision trees are greedy and deterministic, and thus there is a tendency for overfitting of trained data such that the performance of the tree on trained data is bad. Thus, we are trying out a more complex model such as Xgb Boost to try predict the data instead. Xgb Boost is an iterative procedure built using assembled decision tree methods that build a sequence of initially weak models and combine them into increasingly more powerful models using a gradient descent architecture. This is illustrated with the diagram shown here. First, we use the Xgb regressor to create a model based on squared error as the objective. We tune the hyperparameters to ensure efficient speed and good prediction accuracy. We ran our model through tree depths of 1 to 25 to see what kind of difference a deeper tree would make. Also, we have made sure to do cross-validation of 5 folds at every depth. We can see that the Xgb regressor model places a large significance on the older meter instead, which is a stark contrast compared to the significance of year in the decision tree model. For every depth, we can see that the cross-validation matrix seems to indicate that our model is consistent for every set, as the standard deviation is very low, in the 3 decimal place range, and the root mean square error for both test and train set is around 1.1 or less at depth 25. Through the graph, we can easily visualize the fact that Xgb regressor outperforms both models at every depth with lower RMSE and a higher R squared value. Next, we use the Xgb classifier. Using the same process as the regressor, it is evaluated using a loss function of log loss. And you can see the feature importance is also showing roughly the same as the regressor counterpart. The F1 score, which is a general score used for classification matrix, can be seen increasing with the tree depth and peaks at 68% at depth 25. The rest of the scores see similar results. The confusion matrix can also be seen to provide a good amount of true positives and negatives for depth 25, which reflects the F1 score of 68%. Like the regressor, log loss is low, and standard deviation is also low between each fold for all depths, indicating consistency. Now, comparing the two models, we can see the tree classifier has a very bad log loss score as it starts to shoot up after depth 10, which means that the predicted results become increasingly further than the actual. Xgb classifier generally performs better than the tree classifier in all depths. Now, moving on to the outcome of the project. Having solved the 3 sub-problems, we have derived an answer for the main problem, and we have shown that these predictors and response variables are correlated, and we have also shown how different models can affect the accuracy of the prediction. In general, we find that a more complex model, while computationally costly, can give us better results for the same set of variables compared to a simple model. We also found that certain variables such as odometer, state, year, manufacturer remains as one of the few variables with high feature importance throughout the different models we have used, indicating that these are strong predictors for resale price and they should always be considered for the different models. We also found that Xgb Boost model is able to predict the resale price of a car, allowing a seller to price his car at a competitive rate. Hence, if a seller would like to find out a model for him to predict a price of a resale car, he could consider Xgb Boost models. On to what we have learned. We have learned that regression models is not always the best approach, as we have previously discussed on how the linear regression model returned us negative values for the prediction of a resale price of a car. We also learned the concept of how Xgb Boost models work and how we could apply it in these mini projects. There were also a few feature engineering techniques which we have discovered and applied in this mini project to help us pre-process the data. Lastly, our main takeaway was to not blindly fit data sets into models. It is evident on Kaggle that many coders fit their models with data sets that were not clean or processed. And this is bad practice because we have shown how the variables were skewed and filled with a lot of missing data. Now we have come to the end of our presentation and we would like to thank you for your time.